welcome to the group exhibit Hydrogen Fuel Cells and Batteries at the Hanover Fair 2017. We are here at the Technical Forum and my name is Muriel Burkas. Please have a seat, join us, have some coffee and some drinks, it's all for free. I would also like to welcome our guests watching this presentation online through our live streaming. All the presentations are available afterwards on our website if you've missed something the last few days. Now I would like to come to our next presentation. I'm really happy to have him here, talking about ZEG, upscale and commercialization of the technology. Please welcome with me on stage, Senior Engineer of ZEG Power, Dr. Nicola Giulio.
Thank you very much for the nice introduction, and good morning, ladies and gentlemen. So today I'll give a brief presentation about the upscale and commercialization of the ZEG technology. For those who are not familiar with our system, it's a system for high-efficient co-production of electricity and hydrogen from hydrocarbon gases with integrated CO2 capture. It is formed by two core technology. The first one is a solid oxide fuel cell for electricity production. And this works with the hydrogen produced by a sorption-enhanced reformer. That is a modified reforming technology that includes CO2 solid sorbent, which is normally calcium oxide based. And to regenerate this sorbent, we use the waste heat from the solid oxide fuel cell. So we can say that these two core technologies enhance each other, and their close thermal integration is the key to achieve very high efficiencies. ZEG Power was established in 2008 as a joint venture between two Norwegian research institutes. We're a Norwegian company. We're based in Norway, close to Oslo. And we started with the verification at lab scale of the basic technology elements. Then in 2010, in cooperation with different partners, including industry like Statoil, we have concluded the first technical economical feasibility analysis and some modeling and system design for the technology, which brought finally to the construction of a first small pilot plant in 2000, which has been operated from 2014. And which uses biogas as a fuel. And from here, we have developed a new concept that we call BioZEG, which is also sort of a new branch of the company. I will talk a little bit more about this later. In 2016, last year, we have concluded the pre-engineering phase, we can say, the concept design of a bigger plant. We have upscaled, at least on paper, from 50 kilowatt to 400 kilowatts, which means 200 kilowatt of hydrogen produced and 200 kilowatt of power. Today, I will tell you something more about the sorption-enhanced reforming technology. And that's mainly because in recent times, we have been focusing a little bit more on standalone hydrogen production. I will show you a little bit more about the plans on upscaling at the end of this presentation. So what is this sorption-enhanced reforming? It's a modified reforming technology where we have a first reforming reactor. That's the one on the left. And as I said before, in this reforming reactor, we introduce a CO2 solid sorbent, which through a carbonation reaction captures the CO2. And this allows to move the thermodynamic equilibrium of the reforming reaction towards much higher hydrogen yield. So from this first reactor, we obtain a CO2 lean hydrogen gas with very high concentrations of hydrogen. Of course, from the carbonation reaction, we have said normally the solid are calcium oxide based, so when they react with CO2, they form calcium carbonate. This calcium carbonate has to be sent to a second reactor to be regenerated. First of all, to release the CO2 stream, and second, to regenerate the solid and send them back to the reformer. In this reactor, we need high temperature heat, normally between 900 and 1000 degrees C. As I said before, in the full ZEG technology, we provide this heat in a quite smart way by using the waste heat from a solid oxide fuel cell. But in general, if we want to produce standalone hydrogen systems, this heat can be provided in two main ways. One is the direct way. We just feed fuel to the reactor. And of course, we have to use oxygen because we don't want to mix nitrogen with the CO2 gas that we want to release. And the other way is to use an indirect solution. So put a heat exchanger inside the reactor, of course. So what are the main advantages of this technology compared to a conventional one and steam methane reforming? As I said, the introduction of the solids move the thermodynamic equilibrium. And first of all, we don't need any shift catalyst and shift reactor. Everything happens in one single step, in one single reactor. We have hydrogen production, water gas shift, CO2 capture, all in one system. We obtain very high hydrogen yield, above 95% dry basis at temperature of 600 degrees C. You can see this in this graph. This is nothing else that the thermodynamic. You can find this on books. The dotted line is the normal reforming reaction. You have normally temperatures around 700 degrees C and yields around 75%. With the sorption-enhanced reforming, you can lower down the temperature to 600 degrees C, and you can obtain above 95% of hydrogen yield. The CO2 capture is included in the process, as we said. So what you obtain is a simplified and intensified reforming process, which can bring to, of course, cost reduction and energy savings. And for the standalone case, we can reach about 70% of efficiency. In the ZEG full case, including SOFC, we can go even higher than 75, close to 80%. So what have we done about the technology so far, in particular for the standalone hydrogen case? As I said before, we have built a pilot plant. This is what we call the BioZEG 50. It includes also a 20 kilowatt SOFC. But for what concerns the SCR, the hydrogen part, it's a serve reactor that can produce 40 kilowatts of hydrogen, which means around 13 normal cubic meters per hour. We have used dolomite as a sorbent. It's a natural solvent, so it's cheap, which helps. And through this plant, we have established operational knowledge in terms of flexibility of the process, control systems, so startup, rundown, operation, and experience with the technical infrastructure, safety, and so on and so on. We have produced hydrogen, which is kind of a good result. And well, the SOFC have exported electricity to the grid. And we have also verified this thermal integration for regenerating the solid in this second reactor I described before. We have done it in this plant both through the SOFC, but also in standalone mode using a burner, basically. A burner and a heat exchanger immersed in the regenerator. And we have also, let's say, calibrated our existing models with operational data. This is a picture of the SCR plants. You don't see the SOFC here, but this is a dual bubbling fluidized bed, which means that you have two fluidized beds, and the solids are recirculating between one and the other. You can see the one is in the center, the one is a bit on the left, the two white ones. And this is located at Hiner Lillestrøm Hydrogen Fuel Cell Test Center, close to Oslo, where we are also. In 2016, we have completed the pre-engineering concept design phase of a 700 kilowatt SCR system, which could produce around 20 kilograms per hour of hydrogen. Here you have the 3D rendering. This is the heat exchanger that will be inside the regenerator. Of course, we are trying to improve the technology. There is always work to do there. And the focus is on the two reactors design. We want to make them more compact so they can be cheaper. the heat transfer is one of the keys to make this technology competitive. We are studying different options, both for direct and indirect heat transfer. And one of our mother, let's say, research institute, IFE, the Institute for Energy Technology, is working a lot on the optimization of the CO2 sorbents for improved capacity, stability, and lifetime. This is mainly because the sorbents, even though the dolomite is a good solution, is a cheap solution, as you see from that graph, going on with the cycles, the absorption capacity normally decreases. They have been developing synthetic sorbents, and that's the second line that can have, for many cycles, very stable absorption capacities. The objectives are to increase the efficiency from around 60%, a little bit more that we have these days. We're talking about standalone hydrogen production here, to around 70%, and to maximize the CO2 capture to close to 100%. We are doing this at present with a new project. We have started now in April 2017. That is a national industrial innovation project. And we're working together also with the industry on this. So, we love to improve the technology and to study new solutions, but we are a company, so we will pretty much like also to sell. So what is the next step? We are planning to build, in the next couple of years, a real demo plant, a sort of proof of scale, to produce, to have a standalone hydrogen plant from producing hydrogen from biogas. Why do we like this bio-ZEG concept? First of all, because it matches very well with the scale-up of the technology. We can produce hydrogen locally, and this can be used, for example, for transportation purposes. And furthermore, the hydrogen can improve also the biogas production process. In fact, if we inject hydrogen into an aerobic digester, we can increase the methane yield and reduce the amount of CO2 in the biogas, which is kind of a good match. We can avoid separating the CO2 through, for example, scrubbing, when the biogas is upgraded to biomethane for transportation purposes. We can use directly raw biogas into the SCR and obtain hydrogen, which also reduces cost and makes things easier. And this solution is also scalable for industrial use, bigger scale. For example, to use the hydrogen in biorefineries for production of liquid biofuels, and for using the CO2 for greenhouse purposes, for example. Last but not least, the bio-ZEG concept gives the possibility of carbon negative energy solution in case we store or use the CO2. This represents the advantages we could have in the case we use the bio-ZEG concept for transportation purposes compared to a conventional use of biogas. The first one on the top, you use the biogas to produce biomethane, so you remove the CO2 by scrubbing, for example, and you use it in a gas engine. The efficiency of gas engines, as you know, are quite low compared to fuel cells, and often we forget that even if we use biogas, we are still emitting NOxes. So that affects local environments, of course. In the case we use a bio-ZEG system, first of all, part of the hydrogen can be used to improve the methane yield in an anaerobic digester, so we already have an advantage there. And furthermore, once we have produced the hydrogen, we can send that to a fuel cell, and everybody here know that that's a much more efficient way to do things. Furthermore, the bio-CO2 can be used once separated by our system for different applications, for example, for methanation or other. So, as I promised before, I will say a few words about our upscaling plans. Between 2014 and 2016, we have been dealing with this little pilot, 50 kilowatts. That was a sort of proof of concept that gave us a lot of experience on building plants. We plan in the next 2 years to build a first, what we call ZEG2H, ZEG2 hydrogen, for standalone hydrogen production, a first demo plant of around 700 kilowatts. That means, again, 20 kilograms of hydrogen per hour. This doesn't mean that we have abandoned the full ZEG concept, not at all. In fact, we plan to follow 2 parallel paths in the next, let's say, 5 years. We plan to scale up the ZEG2H concept for standalone and also have a first proof of scale, so the ZEG Power demo, including SOFC on a 400 kilowatt scale. We have done already some work in terms of concept design for this plant. And for the future, both have a standalone hydrogen production and co-production at industrial scale. So these 2 paths will be parallel, we'll say. And finally, I want to thank you all for the attention. We are at booth B60 together with other Norwegian companies. So if you come to visit, you can have also an idea on what is happening there in the north. And thank you very much.
Thank you, Nicola. Are there any questions from the audience? Not so many. You've mentioned the road to 2021. When will you think, I mean, you said you're a company, so you want to earn money as well. When do you expect that this stage will be reached? Right now, you're still proof of concept and starting 2020, or?
Well, the idea is already to work with a customer for this first demo plant. And the plan is to have it built by 2019. It should take a couple of years. So that will be already a commercial product. And of course, it will be a matter of working with possible customers to get the best business case by case. But that will be already a product. So we plan to have the product ready by 2019.
And you've mentioned many Norwegian companies or institutions. Your focus right now is national in Norway, or are you already planning on expanding?
Well, we are a technology development company, so we are always looking for improvements and cooperation with both industrial partners and institutions. So for this project I mentioned, that's more related to industrial research, involving also company. But we are involved also in EU projects, international projects. We are cooperating with companies in the US, in Canada. So we are, of course, interested in both things, the commercialization, having a strong network of industrial and commercial partners, but also we are very open to research. And again, actually both of our bigger owners are still research companies, so we have daily contacts with the research environment.
Thank you very much, Dr. Nicola Di Giulio. If you have further questions later on or want to discuss the topics, go to booth B60 on the left side. Thank you very much. The next presentation will start in about 3 minutes regarding the topic sodium nickel chloride battery back in the market with Dr. Matthias Schulz from the Fraunhofer Institut für Keramische Technologien und Systeme. Please stay with us, have some coffee, have some refreshments, and see you in a minute. Thank you very much.